Hello and welcome to another neural TensorFlow video. My name's Ian, and today we're going to talk about activation functions. Briefly kind of talked about them before. They're just nonlinearities that you put at the end of your layer to be put into the next layer. And we use activation functions to kind of break up our data to help it train. Okay, so the first one that's been used around like the 80s up to about 2012 was the sigmoid function. And let's see if I can draw this. Okay, that should be a little more centered, but maybe you get the idea. So it's that kind of S shape, I guess you could say. And what this does is you put an X value in and it shoots out a Y value between 0 and 1. And it's kind of like a logistic probability, which is why it was used. Now, the problem with sigmoid functions is not in the forward pass when we're doing it. The problem comes when we're doing back propagation. So remember, at each point we're calculating the gradient at that point. So what would be possible derivatives or gradients in this function? Well, just kind of think of like the slope. See, in the middle it doesn't really matter, but when x goes to infinity, you're going to find that the gradient is going to get closer and closer to 0, and the same with when x goes to negative infinity. So what would go wrong if we have a gradient at 0? Well, remember when we use the chain rule in backpropagation, we multiply all the previous gradients with all the gradients going backwards. So if we have one gradient that's like 0.001 and we multiply it by any number, we're going to be shrinking that number. And when that number is small, we're going to go backward again, and all the gradients up to the beginning are going to get closer and closer to 0. And this is called the vanishing gradient problem. And this is one of the things that held neural networks back for a while. So that's the vanishing gradient problem, and that's why you should try to avoid sigmoid functions. Or don't try to avoid, just straight up avoid. So that's why we don't use sigmoids now. Now there's also tanh-h's, which are very similar to sigmoids. Instead of putting it between 0 and 1, we go between -1 and 1. But it's the same kind of S shape. But so we still get the same kind of vanishing gradient problem. The one people use today, the most common, is the ReLU, the Rectify linear unit. And that's just a simple line for the positive, and it's going to be a 0 for our negative. And it kind of looks something like max of 0 or x. That's ReLU of x. So ReLU of x is going to equal the max of 0 and 1. And just to kind of think of it simply, gets rid of negative numbers, and that's kind of how it mixes it up. Now, what would be the derivative of a sigmoid function? Well, it would either be x or 0. So the derivative of x or 0. So the derivative of the ReLU function is either going to be 1 or 0. Now, we just talked about how a very small gradient could be a problem. So why do we use something that can possibly give a gradient of 0? And it can happen. It does happen sometimes. But the thing is, it doesn't really happen that often. But if it does happen, it's going to kill your net. So every layer that comes before it, everything's going to have a gradient of 0, and nothing's going to update. And that's a bad thing. But like I said, it doesn't really happen that often. It can happen if you initialize your weights really small, so really close to 0, and then another gradient adjusted and it goes down. But another reason would be your learning rate's too high, so you make a adjustment in the negative direction, and then it goes too large, and then you get a negative gradient, and then your derivative is 0. So that's things to look out for. one of the ways people kind of avoid that is they use a leaky ReLU. And instead of max of 0, it's like, basically, let's do it this way. You get a very small slope. And if it's, so you're looking instead of max of 0 and 1, it's the max of like 0.001 x or x. And this number you choose is a hyperparameter, so you choose it yourself. It doesn't have to be this number, it can be any size. Just make sure it's, you know, less than 1, or else it'll affect this one. So, and then worst case scenario would be a very small derivative when we're going back. There's another thing where I forget what it's called, but instead of a set slope, we have a parameter, and this parameter is when we adjust it when we use back propagation. So this slope can like move up and down during training. I've never seen anyone use it or talk about it, but also like seeing a leaky ReLU is relatively rare because ReLUs are pretty safe to use. You will see leaky ReLUs if you do reinforcement learning or GANs, the generative adversarial networks. You'll see it when classifications, the loss function is usually pretty stable. But in other networks, other architectures, you can get a loss that can have very high variance, in which case you would want a leaky ReLU to give you a buffer. But, you know, don't worry too much about it. Just stick with the ReLU. There's also some other ones very similar, like instead of having a quick turn, it kind of like smooths it out. Again, I've never seen anyone use that or read any papers about people using that. So, you know, take away from this, just use a ReLU. Then you have to be aware that your output values can be quite large. So you could usually throw like a softmax function at the end to get it if you're classifying things with probabilities. But other than that, I guess that's it for today. Thanks for watching. Like, subscribe, leave a comment, and eat a full breakfast.